Okay, are there any questions, comments, concerns? Pose fears? You guys probably want to see this stuff now, don't you? So you have a homework over inverse Fourier transforms. It's up now. It's due Friday at midnight. So go to Blackboard, check that out. It's pretty easy. We got that. We got that. We got that. We got that. We're recording. All is well. Yeah. And then on Friday, I'll cook up a Python project for next week. So if you have any ideas for what would be fun to do in Python, holler at me. It's probably going to have to be something where you like take a signal, Z transform it back, plot the region of convergence. Who knows? All right. If there are no questions, let's just jump right in. So we are out of, what was that, chapter 3? What was chapter 4? Whatever chapter we're in. We're in the next chapter. I think it's 4. But anyway, what we're going to talk about now is for the next couple of days, we're going to take a break from transforms and the like and talk about sampling. It is chapter 4. It says right here, chapter 4 in my notes. So some things that we're going to talk about in sampling are some effects of sampling. Really just like if we change the sampling rate, if we change the way we sample our signal, what sort of weird stuff does that do to our signals? Biggest one that comes to mind is always aliasing. That's what we could do. We could write an anti-aliasing script. Although that's like Serap's pattern rate class. We're going to talk about the concept of sampling, then processing, then what they call reconstruction, which is like the sort of full loop there of discrete time processing. Then we're going to talk about multi-rate signal processing. It is possible to either change the sampling rate on the fly, or maybe work with signals that were sampled at different rates, and sort of what you can do with that and what gets weird about that. So multi-rate signal processing. We're going to talk about analog to digital conversion and the things that come along with that, such as like quantization error, all the ways that AD converters kind of suck, and then finally we'll kind of wrap up with a discussion of oversampling. This is not what we're going to talk about today. This is what we're going to talk about for the next like 2 weeks. Today we're just going to introduce sampling as a concept. And we've actually already talked about sampling as a concept when we talked about periodic sampling. And we had this expression, that our discrete time sequence is equal to some continuous time sequence that's a function of nt, where t is the sample rate, the sample period. We're just going to call it the sample rate. So this is what maps our continuous time system onto our sequence. Now we're going to model this concept of sampling through what's called a continuous to discrete time converter. Or for short, we're just going to call it a C/D, a CD converter. And you can think of the CD converter as the ideal sort of physics class, perfect spheres in a vacuum version of an analog to digital converter. It is a mathematical model for an ADC. Or more to the point, an analog to digital converter is like a physical implementation. It's an approximation of a CD converter. So a CD converter is our mathematical, like I said, sort of physics, perfect spheres in a vacuum version of an ADC. And we're going to model it like we do a lot of things. It's sort of like a black box, and we're going to wonder what's in the box. So if this is our CD converter, we'll feed our continuous time function of t in. We will set some sample rate, and then we'll get our x of n, which of course is equal to x sub c of nt. So that's our model that we're going to mess with. Now, the CD converter is really only defined by setting the sampling rate. At least for now. Which means that we model CD as what we're going to call a sampling function. And the sampling function looks like this. The sampling function is a continuous time, so it's an S of t. It's a continuous time function, which is just equal to the series n equals negative infinity to positive infinity of delta functions shifted by that nt value. Now it's sort of important to note that this is the impulse function. Not the sample sequence. All right, we've been working with the sample sequence, which is not equal to the impulse function, despite the fact that we use the same symbol to denote each one, and they do exactly the same thing in their time domains. And really all we're going to do mathematically is just multiply the signal that we want, or the signal that we're looking at, by the sampling function. So we would say this, that x of s sub t, which is our sampled signal, despite the fact that it's still continuous time, is just equal to x of c of t times s of t. So that's our original signal multiplied by our sample function gets our sampled signal. And like I said, all of these are still in continuous time. We could dig into it just a little bit and say that this is all going to be equal to what? X c of t times our definition for n equals negative infinity to positive infinity of delta t minus nt. And since x sub c is not dependent upon n, we're actually going to bring it into our expression. Ct is equal to the series n equals negative infinity to positive infinity of x sub c of t times delta t minus nt. Now the reason we want to do that is because we want to take advantage of a property of the impulse function that you may have learned about in your linear systems class, you should have learned about in your linear systems class, which is called the sifting property, which states that if you multiply some function x of t times the impulse function at t, what you're going to get is just x at 0 times delta t. This is sort of the mathematical root of the impulse being a sampling thing. So what that does for us up here is this. It says that s of t is equal to the summation negative infinity to positive infinity of, let's see, we had x of t, or x of c of t times delta t minus nt. That's going to convert our x of c into x of c times nt. It's going to effectively make it a function of n and tie it in t minus nt. So there's our full definition for our sampled continuous time function. So from there, we're going to expand on our model for our CD converter. Expand on the CT converter model. So we'll still have our signal x sub c, our continuous time signal x, coming in. Except now we're going to put in the box our sampling function, s sub t. We're going to multiply them together to get our x sub s of t. And then we're going to put it in another box. Which converts from what we call an impulse train to a DT sequence. And the output we'll get here is our x of n. What happens in this box is not super duper important, but the idea is that the multiplication converts everything to a train of impulse functions, and then we're just going to sort of convert those over to our samples really fast. So let's kind of model what that looks like. And that'll be the last thing we do today, actually. So let's say that we've got a signal here. This is in time. We got some ticks. We'll say that one of these is 0, and that's t, and that's 2t, and that's 3t, and that's minus t, and minus 2t, and minus 3t, and minus 4t. And let's just say that we have some signal. That's our analog signal x sub c of t. Now from there, what happens is we create a train of those impulse functions. Let's see what's happening here. Fine, you win. just like that. So that's our impulse train, x sub s of t. Now what happens is this then gets converted into our discrete time sequence 0, 1, 2, 3, 4, 5, 6, 7, 8, which is going to look a lot like, let me use purple. Trying to kind of model what it looks like up here as best I can. Okay, so that's our sequence, x of n. And let's do this instead. I'm going to copy, I'm going to try to copy, if OneNote will let me, the original bit that we started with. Let's do that. And let's lose our original impulse function here. Okay, so in the first example, we said that our sample rate was equal to t, right? We took a sample every t seconds. Now let's double it. Let's see what happens if we take our sample rate equals 2t. So we're still going to sample at 0, like that. Now we'll sample at 2t. We'll sample at minus 2t. We'll sample at minus 4t. Just for fun, say that that was 4t right there. Well, now what's going to happen if we take our x of n and lay it out. There we go. Come on, cooperate. And make our tick marks. And we'll say that's still 0, and that's n. That's 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. Back to purple, our 0th sample is that. But our next sample is the one that's at 2t, right? Which is that. Our second sample is the one that was at 4t. Like that. Our minus 1 was the sample that was at minus 2t, which is up here. So that's all we got just from that snapshot, and we don't even know what the rest of these are. So the punchline, the take-home message there, is that the sample sequence contains no information. about the sample rate. And so it's important to pay attention to it, because if you look at these two sequences, let's zoom out a little bit. Despite the fact that we sampled the same signal twice, our output sequences, x of n, are very different, right? So, and then there's no way to know that they are different just by looking at x of n. When you just have your signal that you've got, there's no way of knowing how it was sampled or anything like that. It's just everything is in terms of samples. Does that make sense? Cool. Right on. So, that's actually all that I've got for you guys today. On Friday, we'll start to dig into some of this aliasing business, and we'll kind of keep it going. And we'll get a Python project, maybe to do with some audio aliasing, I think. But I'll look into it. All right. So if there's nothing else, thank you so much, guys. Enjoy getting out 20 minutes early, and I'll see y'all on Friday.
Tell you guys about how we potentially might not be doing in-person classes after Thanksgiving?
Yeah, if I know me.
He said he didn't know, so he said plan, he said pictures.
They sent out that poll, the student government sent out that poll.
Yeah, he said it might not be done, but then we don't spend any time in the lab because our project's mostly software.
Well, he told the greenhouse group was like, wait, you're telling me we have to now finish 2 weeks early?
Yeah, I was thinking about potentially